Hello, in this video we're going to be taking a look at the solutions to AP Physics 1 homework, Forces at an Angle. Remember to pause or rewind the video as needed. Let's begin. Number 1. The diagram shows a box of mass 30 kilograms and 3 ropes that are part of a system in equilibrium. The angle theta equals 37 degrees, so that the sine, cosine, and tangent of 37 can be found in the AP Physics table of information, can be used to get whole answers. These values that can be used later, the sine of 37, according to the trig table and the table of information, is 3/5. The cosine of 37 is 4/5. And the tangent of 37 is 3/4. Okay, so before we get into actually doing the question, it would probably be best to sketch out all the forces at work and everything going on the diagram here. Let's do that. You're going to be sketching out the forces on this junction that contains all 3 of those cables. Okay, let's see what those would be. We would have tension 2 going to the left, tension 1 going up the rope, and tension 3 pointing straight down. Now, since tension 3 is also pulling up on the mass with weight mg, what you can do is just cut out the middleman and say tension 3, really you just have weight pulling down. And so that's basically what we're going to do, is we're going to factor into, oops, erased too much. We're just going to say the force that's pulling down on this is the vertical weight. We have components of T1 going over to the right and up. And this angle here is the same as this angle here. Since this is the adjacent side of the triangle, we go hypotenuse, which is T1, cosine of theta. And since this is the opposite side of the triangle, we go T1 times the sine of theta. Let's use this information to put together our equations for part A. Part A, write 2 equations relating the values of mg, theta, T1, and T2. One should represent horizontal forces balancing, the other should represent vertical forces balancing. Then solve the equation to obtain the values for tension 1 and tension 2. So let's split this area in half. Your vertical forces would be force going up because we're not accelerating. This object, this mass is in static equilibrium, no acceleration. And force going up equals force going down. Now, what force is going up? Well, the only force going up is this one here, T1 sine theta. The only force going down is weight. So T1 sine theta equals the weight. And you can solve this by dividing both sides by sine theta. T1 would be equal to, now the mass was 30 kilograms, and I'm going to let G equal 10 in this one just to make the numbers a little easier to work with. It's not a lab-based question, so in questions that are not lab-based, simply make G 10. So I'm going to go mass of 30 kilograms times 10 divided by the sine of 37 degrees. Now we established from the trig table, the sine of 37 degrees is 3/5. You could always put that in your calculator to see that for yourself. But we have 300 divided by 3/5, which is 0.6. And dividing those two, we get 500 newtons. Okay, now in the y direction, we're not balanced. In the x direction, we're also balanced and not accelerating. So, but this time, it's forces going left equal forces going right. Forces going left, according to the picture, would be T2. So T2 goes left, and T1 cosine of theta goes right. Okay, we already know what T1 is. Now we need to find out the value of T2. So T2 is equal to T1, which is 500 newtons, times the cosine of 37 degrees. We established that that is 4/5, or 0.8. So we're going to go 500 newtons times 4/5. You can see this is going to cancel a little bit. 5 goes into that 100 times, and you are left with 400 newtons. Okay, now you can start to see in the dot below, okay, and the dot below represents the joint where the 3 ropes join. Each box represents 100 newtons. So draw the forces according to scale where the 3 ropes join to where they join. So T2 is 400 newtons, so we're going to draw 4 units to the go. 4 units to the left. Okay, now we're not drawing any of the components, but remember you have this component here and this component here. So we know this component also has to be 4 units because it's balanced. We also know the weight vector is going to be 300 newtons because it's 30 times 10. So 300 newtons would be 3 boxes going down. Lastly, we have T1. Well, if it's 3 boxes going down, it's got to be 3 boxes going up and 4 boxes going to the right. So you're going to make T1 be exactly 4 boxes this way to balance the T2 and 3 boxes this way to balance the weight. And there we go. To increase the amount of force T2, would you have to increase or decrease the angle? Would this also change the value of T1? And if so, how? Answer these questions and explain your reasoning below in a well-organized paragraph. Draw a new free body diagram for the changed angle on the grid below. Use it to support your reasoning. Well, a couple of things that we should note here. Weight is still 300 newtons, okay, or 3 boxes down. The weight didn't change, so that's still going to be 3 boxes down. But what's going on here for T2 to increase then the horizontal component of T1 would also have to increase. Okay, so let's see. If if T2 increases from, let's say, 4 units to 5 units, then we draw this 5 units this way, but that means that the horizontal component of T1 is now 5 units, while the vertical is still 3 units to balance the weight. So that means you're going to draw tension in this direction here. 5 units this way to balance T2, increase, and 3 units up to balance the weight that still remained the same. Okay, this means theta would decrease. Right, this angle is now a little bit smaller than this angle because you're stretching out T1 farther horizontally with the same vertical rise. Number 2, a force of 500 newtons is applied to a 50-kilogram block at an angle of 37 degrees to the horizontal. The coefficient of kinetic friction between the block and the table is 0.50. Again, let's make sure we draw the forces acting on the block before we proceed. Well, you've got the force already drawn, so let's draw the components. You've got a horizontal component, a vertical component. The horizontal component is F cosine theta. The vertical component is F sine theta. You have a normal force and a weight, and you have friction pointed to the left. Don't yet know if the object is accelerating. It didn't tell us this so far. Oh, yep, it's accelerating. Since the block's accelerating this way, that would make this the causing force of acceleration, and friction would be the opposing force of acceleration. So, part A, the dot at the right, draw the forces, not components, acting on the block when it slides to the right. Each box represents a 100 Newton grid, so your forces must have exact lengths and angles. In the space to the left, write a narrative in which you explain how these forces were calculated, using what equations and in what order. Well, a couple of things. The force of, the block itself is 50 kilograms, so the weight is going to be 50 times 10, or 500 newtons. That's 5 boxes down. So let's draw that. We have the weight going 5 boxes down. You have the normal force. Okay, now the normal force is a vertical force. Okay, and in the vertical direction, forces up equal forces down because you're not accelerating vertically. Now, how many forces are going up? Well, if we look at the picture, normal force goes up, F sine theta goes up. Weight goes down. So normal force plus F sine theta equals the weight, mg. Solve for the normal force by subtracting F sine theta from both sides. And the normal force, which is equal to mg minus F sine. So this is going to be mg, the weight, or 500, minus the force, which is 500 sine of 37. Now, sine of 37, well, that's going to be 0.6. So that would be 300. So 500 minus 300 would be 200 newtons going up. So the normal force is only 2 units going up. And then lastly, friction. Friction is fun, mu times the normal force, and mu, we were told, is 0.5. So 0.5 times the normal force, which is 200 newtons, means the friction is 100 newtons. So we're going to go one box to this way, to the left. Okay, now how do I draw the tension force, the applied force? I know that in the horizontal direction, let me see here. If we have 500 and we have an angle of 37, so 500 with an angle of 37, so 500 cosine 37 would be 400 going this way, and 500 sine 37 would be 300 going this way. And you should see it as a 3, 4, 5 triangle. So I'm going to go 4 units over, 3 units up, and my force would be pointing this way. Again, not components. Calculate the acceleration of the block, well, the box. So acceleration, I'm thinking I'm going to use Newton's second law. Since we're accelerating masses and forces, so we have causing force minus opposing force equals ma. That would be force cosine theta minus friction. Equals ma. Divide by mass, okay, and we've got the friction. So it's force cosine theta minus friction over the mass. Now force cosine theta, if you remember, was 400 minus friction, which was 1 unit or 100 newtons. And divide that by mass of a 50 kilogram block. And 300 over the 50 gives us 6 meters per second squared. Number 3, use the diagram for question 2 for this question as well. The diagram shows a block of mass m that is initially in motion and pulled across a table by a force F directed at angle theta. There is a non-zero coefficient of friction, a non-zero coefficient of kinetic friction between the block and the table. Let this be case 1. And a student measures the acceleration of the block A1 in this case. The student in case 2 increases the angle slightly but keeps the angle below 90, measures the new acceleration of the block. A. Is it possible for A of the second case, A2, to be greater than A of the first case, A1? By discussing specific forces and components, explain why. Part B, is it possible for A2 to be greater than A1? By discussing specific forces and components, explain why. Well, if theta increases, then F cosine theta decreases, the horizontal component of the applied force, which decreases the net force and thus A2. Therefore, A2 would be less than A1. A2 is decreased. Is it possible for A2 to be greater than A1? Well, again, let's see. If theta increases, normal force decreases. This happens because there is less force applied from the surface to the object. Well, the implication of this is less normal force means less friction. Which means a greater net force. Just think about it. If you have less friction, then you're subtracting less. You're less opposing force. If the opposing force and you're subtracting less from the causing force, that means your overall net force is greater. Greater net force and acceleration. Just remember, if net force goes up, acceleration goes up. Net force goes down, acceleration goes down. Right? That would tell us that A2, for A for the second case, would be greater than A for the first case. Number 4. In both cases shown, a 10-kilogram block is set on an incline with 53 degrees. In case 1, the block is on frictionless rollers, and in case 2, the block has a coefficient of friction with the incline of 0.3. Part A. Calculate the acceleration of the block in case 1. Show your work in narrative form. Explain in words what you are doing along with showing calculations. Include a free body diagram with components to show as part of your explanation. So let's draw this over to the side. Now, here's the incline. And what we typically do for inclined planes is we take what would normally be the horizontal direction, I don't say X, right? Horizontal direction and the vertical direction, and we take them and we just kind of rotate that so that the horizontal direction goes up and down the plane and the vertical direction you can see is going in and out of the plane. Now, what forces are acting on this mass? Well, you've got the weight going straight down. You've got the normal force perpendicular out. You've got the components of weight, which go opposite the normal force and parallel to the plane. Which means if this is the angle of incline right here, that's also the same as this angle here. This is the adjacent component of the weight mg, therefore this side is going to be mg times the cosine of the angle. The side pointing downhill is the opposite side of the angle, which would be the hypotenuse mg times the sine of the angle. Now, since the object is accelerating downhill, mg sine, right, is the causing force. Since nothing is going uphill, there is no opposing force. We're going to use Newton's second law. Causing force minus opposing force equals ma. Well, the causing force is going to be mg sine minus 0, because there's no opposing force, equals ma. Well, to find the acceleration, we just divide the mass. You can see it cancels both sides. And so A is equal to g times the sine of theta, or 10 times the sine of 53 degrees. And 10 sine of 53 degrees is 8 meters per second squared. Part B, calculate the acceleration of the block in case 2. Show your work in narrative form, this time only explaining what you must do differently from part A in order to find the acceleration. Okay, so what you had before is you had net force must point downhill because that's the way you're accelerating. Acceleration and net force point the same way. And the only force pointing downhill is the component of the weight, mg times the sine. That is still going to be the case. Okay, so again, our free body diagram is going to look very similar. In fact, I'm just going to go ahead and copy it. Okay, but the biggest difference is there is an opposing force this time because now there's friction going up the plane. Friction is fun. Okay, and the causing force is going to be mg sine, and the opposing force is going to be friction. So just like before, in the y direction, you're not accelerating. So that means normal force still balances mg cosine. So let me see here. Forces going up equal forces going down. For the y direction, we're talking about the vertical direction, and normal force balances weight cosine theta. In the x direction, you are accelerating. Horizontally, you are accelerating, so we're going to use Newton's second law. Causing force minus opposing force equals ma. That would be mg sine going downhill minus friction going uphill equal ma. Okay, well, we have some substitution to do here. So we have mg sine minus mu times normal force. Notice, ladies and gentlemen, I'm substituting friction for mu times normal force. Equals MA. Now in my next substitution, I've got mg sine minus mu mg cosine. Hopefully you all see that I'm substituting normal force. I'm substituting normal force for mg cosine. So a lot of substitution here, okay? And that, of course, equals MA. Notice there is a mass in each term, so the mass would divide out. In fact, I'll just go ahead and divide each term by mass, okay? And we've got our acceleration that we can plug into. Acceleration is going to be g sine theta, which would be 10 sine of 53, minus mu, which is 0.3, times g, which is 10, times the cosine of 53. Well, 10 sine 53, that would be 8 that we got from before. But this time you're subtracting the friction part of it. And this part comes out to 1.8. So the acceleration has gone down as the net force has gone down as friction has increased. Part C, if masses in both cases were increased to a new greater mass, big M, how, if all, would change your accelerations found in part A and B? Well, as you just saw me cancel the mass from each term right here, that would be a pretty clear sign that there would be no change in acceleration. Okay, why? Well, the mass cancels out. It's mass independent. Number 5. A wooden block is set on a wooden board. You are asked to determine the coefficient of static friction between the block and board. You simply gently increase the angle of the board until the block begins to slip and then measure that incline angle theta. Is this enough information to determine the coefficient of static friction? If so, explain how to use the angle and not explain how to use the angle to find the coefficient of static friction, including a free body diagram with components. If not, state what else must be measured and then explain how to use the angle in those measurements to find the coefficient of static friction. Let's see. There's the object. You've got the weight, and this is the incline, angle of incline. Got the normal force coming out. You've got the component going into the plane, the component going down the plane. There's the angle of incline, or same as the angle of incline anyway. This component is mg times the cosine of the angle. The hypotenuse is mg, the weight. The component going down the hill is going to be mg sine theta, and friction would be going up the hill, and friction is fun. Okay, let's take a look at this right here. In the vertical direction, force vertical, forces are balanced. And forces going up, that means out of the plane, equal forces going down. Okay, and what that should tell you is that the normal force balances mg cosine. Now, static friction means we are not moving. We're not moving in either direction, x or y. So horizontal forces would be forces left equal forces right. Left goes down the plane, right goes up the plane. Forces going to the left would be going downhill, and that's mg sine. Equal forces going to the right, that's uphill, that would be friction. We need to do a bit of substitution here. We're going to first substitute for friction. So we have mg sine equals mu times normal force. But then, ladies and gentlemen, we need to substitute for normal force. Normal force was mg cosine. So mg sine of theta is equal to mu times mg cosine of theta. Now, to solve for mu, you need to divide by the mg cosine. And mu is equal to, notice masses cancels, g's canceled, it's equal to sine over cosine, which actually turns out to be the tangent of the angle. Mu sub s depends only on theta, at least when we're not accelerating here. And finally, number 6. A person on an airplane, initially at rest, holds a watch on the end of a string. When the airplane accelerates to take off, the watch makes an angle theta with the vertical as shown, as measured by a protractor. Draw the forces to explain, draw the forces acting on the watch, including components at this time, then explain how this setup, along with a calculator, can be used to determine the takeoff speed of the airplane. Discuss the specific calculations, equations, etc. that must be made. Well, first let's draw a free body diagram on the watch. You've got the weight going down, and you've got tension going up. But you've got a component of tension that goes up and a component of tension that goes over. This angle theta is the same as this angle theta right here. The vertical component of tension right here is the adjacent side of the triangle, so that would be tension times the cosine of theta, and this is the horizontal component of tension is actually the opposite side of the triangle. That would be tension times the sine of the angle. Now, up and down are balanced. The t sine theta points in the direction of the plane's acceleration. That is our net force right there. So let's break down some of these ideas. Number 1, downward weight balances upward vertical component of tension, t cosine theta. So we have t cosine theta equals the weight, and the tension is equal to mg over the cosine of the angle. And again, the angle is measured using a protractor. Using Newton's second law, causing force minus opposing force equals ma. The causing force would be your T sine. There we go. There is no opposing force because an opposing force would be pointing the opposite way. So using Newton's second law, we have causing force minus opposing force equals ma, but there is no opposing force. So we have T sine theta as our net force, and that's equal to ma. Now, we want to be able to solve for acceleration. Now, to get the takeoff speed of the plane, we need the acceleration. So first, we can substitute the value for tension, mg over cosine, in for tension right here. And so we get mg over cosine equal times the sine right here equals ma. You'll notice the masses divide out on both sides, and sine divided by cosine, in case you forgot, is tangent. So acceleration is actually going to be g times the tangent of the angle. So you can get the acceleration by multiplying 9.8 times the tangent of the angle created with the vertical using the protractor. Then we can use the equation V equals V naught plus AT, where V naught is 0 because the plane takes off from rest, and V equals the acceleration of G tangent of theta times time would give you the takeoff speed. Okay, and this is where V naught is 0 and T is found using a stopwatch.